Okay, great. Let's start. Hi, everyone. My name is Puzi Liu, and it's a great pleasure to be here and share your recent work, Robot Reinforcement Learning on the Constraint Manifold. I would like to thank my colleagues, David Tatel, Haitham Bouammer, and Jan Peters. In robotics application, the robot needs to interact with the human and the environment. So one important problem that cannot be ignored is safety. The robot should not harm the human, the environment, or themselves. In particular, we want to ensure that the robot behaves safely at any moment. So the key question that we want to answer here is, how can we ensure the safety during the reinforcement learning process? We believe that it is beneficial to leverage our expert knowledge in the safety-critical environment. In robotics, the kinematics and the dynamics of the robot is usually well studied, and the constraints can be predefined. If we can integrate this kind of information into the reinforcement learning process, we are able to develop safe exploration algorithms. So the safe exploration problem can be formulated as follows. The objective is to maximize the cumulative discounted reward. And we consider the stepwise constraints in the equality constraints and inequality constraints. Please note that we separate the state variable into the controllable state, which is Qt, and uncontrollable state, which is Xt. And in this case, we only focus on the controllable state here. Our idea to solve this problem is like we're first trying to construct a constraint manifold, which is this green surface. And then we can determine the tangent space at each point and also its linear basis of the tangent space. If we know this tangent space, we are able to construct a tangent space velocity that tries to enable us to move on the manifold. Okay, based on this idea, we developed the ATOCM method, which is acting on the tangent space of the constraint manifold. Firstly, we construct the constraint manifold by adding a slack variable into the inequality constraints, which is CQ equals to 0. Then we can calculate the time derivative of the constraints, which results into the Jacobian times the velocity. And we can also determine the non-space of the Jacobian, which this non-space represents the linear basis of the tangent space. Using the spaces together with the coordinate alpha, we are able to construct the tangent space velocity. We can easily prove that using this alpha, we are able to ensure that the velocity of the constraint violations is equal to 0, regardless of the choice of the alpha. These two equations are the key concept of our method. So we're starting from an initial point that satisfies the constraints, and we choose arbitrary alpha, but we're still able to ensure that the constraint violations equals to 0. However, the original constraints is usually not sufficient to ensure the safety for the robotics. As an example here, that we want to prevent the car to collide with the wall. And the constraints can be defined as the distance between the car and the wall is bigger than 0. But it will be too late to brake if we only violate the constraints. Instead, if we can take this velocity of the constraints into the consideration, we are able to ensure to make an early brake and avoid the collision. Similar on this idea, we integrate the velocity of the constraint function into the original one to construct these viability constraints. Okay, after the similar derivations, we are able to obtain these control accelerations. This control acceleration is composed like two terms. The first term is the tangent space acceleration, that moving on the tangent space of the manifold. The second one is the curvature correction term. After we determine this acceleration, we are able to use an inverse model to determine the actions. For example, in robotics, we can determine this lambda function can become inverse dynamic model when we are controlling the robot torque. But we can also use the Euler integrations to get the positions and the velocity and send them with a sufficient good tracking controller. Let's take a look at how our method working in the discrete time. We're starting from an initial point that on the constraints manifold. And we apply the tangent space action and the curvature correction, we reach to the second point, which is no longer on the R manifold. Therefore, we need to add an error correction term into our method, and which results into the next point, that coming back to the manifold. We refer to the last two terms as a manifold maintenance term. Here is the control diagram of our method. Our agent is able to sample an alpha and determine the non-space acceleration and the manifold maintenance acceleration. And then we use the inverse model to determine the action and put into the environment. Let's take a look at how our method working in the robot air hockey task. This task, we try to hit the puck into the opponent's goal. We define the constraints as the to move the any factor on the table surface. We also add some constraints to control that the joint link does not collide with the robot. And the control action here is chosen to be the joint torque. It can be seen here that the robot is able to explore at the initial epoch to safely safely without collisions. And in the end, we are also able to learn a good behavior in the end. We also extend our method to the partially controllable constraints, which we consider the uncontrollable state into our constraints I would like to skip the derivations, but directly show you the results. In this experiment, we control the control acceleration of the blue point. The goal is to reach the target, and the red dot is not controllable. It can be seen that our method is able to explore every space, but trying to avoid the collision at every time step. And also, in the end, we are able to reach the target. So, as a conclusion, our method trying to act on the tangent space of the constraint manifold. And we also show that our method can handle the equality constraints with a robotic task. We also show that our method can cope with partially observable scenarios. Thanks for your attention. Yeah, I'm happy to take any questions.
All right, thanks very much. Are there any questions here in London? Francesco.
Thanks. The very last part is the one that it's interesting to me the most. Can you say a little bit more about how you take into account the non-directly actuated part? In the video that you show, the red dots are moving on their own. There's no interaction between the controllable space and the non-controllable one, in that case, the red dots.
Yes.
Do you actually take into account the situation where there is a connection between the two? Even though they're not directly actuated, you still have a way to influence the red dots through the movements of the blue dots in that case?
Okay, maybe I can go back a bit with the slides. Yes. If you see here that we construct the constraints function is very similar to the previous one. And we also calculate the time derivative of this whole constraint function, which will result into the Jacobian of the controllable state and the Jacobian of the uncontrollable state. So we also need to integrate this term into this whole manifold maintenance place. So we need to consider also the state of the uncontrollable part and also the velocity of the uncontrollable part. That will be like a very complex term that involves every information that from the states that is not controllable. And then we result into this tangent space and the manifold maintenance term.
So basically the connection between the QT and XT, the controllable one and the non-controllable one, is through the constraints itself?
Yes.
Okay.
Yes,
Thanks.
exactly.
Thanks.
Okay, any more questions? Yes, over there. For those of you at home, do feel free to ask questions on feed loops. There aren't any for this talk, but if you put them in the question and answer session, we will read them out.
I would like to just ask, how is your method connects with the control barrier functions?
Sorry, I didn't really...
How's your method compares and connects to the control barrier functions, which people generally use to specify those constraints?
Actually, we will say that this viability constraint is one class of the control barrier functions. It's basically the linear type of the control barrier functions.
Got it. Thank you.
Yes.
Took my advice and asked a question online. Well done. So the question is, do you plan to do real-world robot experiments?
Yes. Actually, we are planning to do two parts on this part because, as you may know, that there is constraint violations. So we want to firstly try to see how is the upper bound of the constraint violation, such that we have some more theoretical improvement, and then we'll also test on the real robot experiment. Right now, it's some other technical issues on the real robot platform, such that we don't really do the test.
Thank you. And we probably have time for one more question, or maybe a couple more, if there are any. Yes, up there.
Thank you for your talk. So if I understand correctly, you take position and velocity constraints into account. Is it possible to take acceleration or jerk constraints into account in your method, or is it something you plan to?
Actually, it is possible, but then we probably need to go to a higher order. So we probably need to go to the jerk level and then do the integrations or do every other method that's trying to do the control action in the end. Yes.
Thank you.
Thanks.
Time for one more quick question. I can't see any hands. If there are, let me know. Ah, there we go, down in the middle.
Hi, thanks for the talk. I'm curious to know if you have thoughts on how to implement constraints that are more semantic in nature and not necessarily easily to express in XYZ state space.
Yes, actually, that is the most challenging problems, right? Like, if you want to ensure the safety, the problem is how you can define the constraints such that the robot can behave safe. That is also some challenging problems that we are considering in the future, like doing the locomotion and define the constraints to avoid falling down, something like that. But it would be hard to have a general solution of any type of constraints or any type of task.
But would you still be expressing like a Jacobian with respect to some sort of predicted like good, bad variable with respect to your state?
Yes, actually, I would also, we are thinking also about like to learn some constraint functions instead of doing like a hard-crafted constraints. For example, there are some methods trying to learn the constraints manifold, and then probably we can also use that, and with a neural network, we can also get the Jacobian of it.
Got it, thank you.
Yeah, thanks.
Okay, thank you very much, Pitya.
Yeah, thanks.